Hi all, in previous lecture we have studied about the three rotor system and we have analyzed it in detail. So in this video, based on those analysis, we will be solving one problem from this three rotor system torsional vibrations. So here you can see the question, a three rotor torsional system shown as in figure, and here we have to find the frequencies of this torsional vibrations and also positions of the nodes we have to locate. The different properties of the rotors and the shaft are given. The rotors are actually representing the engine, the propeller, those are coming at the end of this shaft, and at the central the rotor is actually the flywheel. So those are named as A for engine, B for propeller, and C for flywheel. And shaft is actually of different diameters, so you will have to use the concept of torsionally equivalent shaft to convert it into a shaft of single diameter. So between this engine and propeller, it is of 45 mm diameter, and on to the next part it is of 40 mm diameter. So we can maintain a uniform diameter, say for example 40 mm throughout. Then you can convert the 45 mm part into 40 mm. So then the length will be changing. That means the 2 meter length will be getting changed to some other value. So that will be our first step to find the torsionally equivalent shaft, and then we will be finding the type of vibrating system, that is the two node system or a single node system. So in this step we will be finding this torsionally equivalent shaft, and here we are maintaining the diameter of 40 mm which is throughout. So here if you are seeing this 40 mm diameter part is having a length of 4 meter in total. So the same will be maintained here also, 40 mm of 4 meter length. But here 45 mm is coming for a length of 2 meter, and we are converting this 45 mm diameter into 40 mm diameter. So this length will be getting changed from 2 to some other value. So you can find this length based on the theta value which is same or which makes it this torsionally equivalent. So based on this we have derived the previous condition in the previous videos. So this is actually the length in the equivalent shaft LE divided by diameter d raised to 4 is equal to the actual length, that is you can say L1. This is 2 meter, so you are converting this 2 meter divided by d1 raised to 4, and this d1 value is actually 45 mm. So here we are maintaining the equivalent shaft of diameter, this is 40 mm. So this value is 45 mm and L1 is 2 meter. So if you are substituting all these values in correct unit, then you will be getting the equivalent length that is coming in here. You will be getting a value of 1.247 meter. So this value will be of 1.247 meter, and the remaining length will be of 4 meter. So now you are having a torsionally equivalent shaft which is having uniform diameter of 40 mm from the left end rotor, that is A, to the right end B, and its length between this rotors where this C is coming also shown. So 1.247 and 4 meters. So this is the three rotor system with which we have to make the analysis for finding the natural frequencies and locate the node. So based on our previous lecture, there are two kinds of frequencies, or there are two types are occurring. One is known as two node frequency, where two node points are coming within this section of the shaft, and in single node type there will be a single actual node within the system, and another node is actually a projected one. So for the analysis, let us assume the two node frequency case where here the rotors A and B are rotating in the same direction, and the rotor C that is coming centrally is rotating in the opposite direction to produce the torsional vibration. So you can represent the variation of amplitude of this theta at different locations within the rotor and within the shaft as shown in figure. So here A and the rotor B are rotating in the same direction, so this will be coming like this, and this C is actually rotating in the opposite direction to produce the torsional vibration. And from this variation you can observe two node points are happening where the effect of torsional vibration is 0 or its amplitude is 0, which is cutting the horizontal axis. So this is one node point and this is another node point. So here you can mark the different length to find the or to locate the node. The node 1 is located from the left rotor A, that is by a distance of LA, and the other distance at the other end will be LB. And this C can be considered as the rotor which is connected to node by a distance of LC1 and to the other node by a distance of LC2. So by doing analysis means you will be evaluating all the values of LA, LB, LC1 and LC2. And here we will be converting this three rotor system into three single rotor system based on this node by considering it as a fixed point. So in previous analysis I have explained all these things. So you can write the natural frequency of the first part with respect to node and which is coming onto the left. So you can write omega na as square root of qa by ia, where qa is the torsional stiffness of that part which is coming to the left of node 1. And that can be written as gj, square root of gj by la into ia, where ia is the mass moment of inertia of the rotor A which is given in the question, and la we have to evaluate. Similarly, you can write the natural frequency of the other part. So if you are considering the last part, that means the part which is coming right to the node 2, then you will be having this LB, which is, and this moment of inertia is IV. You can write square root of QB divided by IB, and which can be expanded to square root of GJ divided by LB into IB. Similarly, this rotor C is coming here, and this two lengths, this is similar to fixed between these two nodes. So you can write square root of QC by IC, where it is the it is like a parallel connection. So you can add the total stiffness of those two parts. So it is square root of QC1 plus QC2 divided by IC, and you can expand it like square root of GJ by LC1 plus GJ by LC2 into 1 by IC, where this LC1 you can write it as L1 minus LA, where L1 is this distance between rotors A and C, and similarly L2 is the distance between rotors C and B. So L1 value is 1.247 within this torsionally equivalent shaft, and L2 is 4 meter, where this shaft is having a diameter of 40 mm or 0.04 meter, which will be required for evaluating the J value which is coming in this equation. So you can equate all these frequencies with respect to each other to find the value or to locate the node properly. Here only unknowns are actually LA and LB. So here one unknown LA is coming, here another second unknown LB is coming, but LC1 and LC2 you can represent in terms of LA and LB. So we will be solving, and that procedure is coming now. So first we will be equating the omega Na with respect to omega Nb, then this will be coming like this, and you can simplify this to form, from where I will be representing this LB as LA into IA divided by IB, where the value of IA and IB is given, which is 30 and 50. So you can convert this or represent this LB finally as IA by IB will be coming as 0.6. So 0.6 into LA will be coming here. And here in the next term or in the next step, you will be equating omega Na with respect to omega Nc. Then finally you will be getting this expression, where you have to substitute all those known values to find the value of LA. You can substitute the value of IA, which is the mass moment of inertia of the rotor A, which is 30 kilogram meter square. You have to substitute all values in SI unit, and this L1 value is 1.247 meter, LA is the unknown, and this L2 is again 4 meter, and this entire term will be coming as 0.6 into LA, and this IC value is actually around 90. So it is 90 kilogram meter square, which is given in the question. So you can simplify these two equations and solve for the value of LA. So this equation will be actually a quadratic in LA. So you can solve, then you will be getting two values for LA. Then here the values obtained are 0.913 meter and 4.821 meter. So corresponding to these individual values, you can find the LB value also, because LB is equal to 0.6 into LA. So for 0.913, you will be getting LB as 0.548 meter. And to the other value, it is 2.893. So there is two combinations of this LA and LB values. And these two combinations will be representing the two node case and single node case. And how you can identify this two node and single node based on the value of LA. Because in this figure, the L1 value was actually around 1.247 and L2 value is 4 meter. So if LA is coming lesser than 1.247, here 0.913 is coming, and LB, which is 0.548, is coming lesser than that 4 meter, then this will be representing the case of two nodes. And the other case, whenever the LA value is greater than L1 or LB value is greater than L2, then it will be representing the case of a single node or fundamental frequency case, where a single node is occurring within the shaft. So the figure with which we were explaining is actually now of this values having LA as 0.913 meter and LB as 0.548 meter, and the other values or its plot I will be showing towards the end of the solution. So this was the one we were explaining where two nodes are happening. So the node location now we are having. So this is the first node. So this is the first node and this is the second node. So first node is occurring at a distance of LA equal to 0.913 meter. So you can find the value of LC1. So this LC1 will be equal to 1.247 minus 0.913. So you can find that value. And similarly, this LC2 will be equal to L2 minus LB, that is 4 minus this LB, which is 0.548. So you can find these values. So these values will be coming around, LC1 will be equal to 0.334 meter and LC2 will be becoming around 3.452 meter. So based on this, next we have to find the natural frequency of this vibration, and also we have to find the relative amplitudes at the rotor. So you can use either of the equation for finding the natural frequency. I will be writing this natural frequency with respect to the rotor A. So you can write it as square root of QA divided by IA, where IA value is given 30 kilogram meter square, and QA value you can write it as G into J divided by LA into IA. So this values you are having. G value is given, which is the rigidity modulus, as 84 gigapascal. So you can write it as 84 into 10 raised to 9 into J, which is pi by 32 into D raised to 4. So this shaft is of diameter 40 mm. So it is 0.04 raised to 4. The whole divided by LA you are having, you have obtained after solving those quadratic equation. So it is 0.913 into IA value was given in question, which is 30 kilogram meter square. So if you are solving this one, you will be getting the value in radians per second, and here the frequency will be coming around 27.71 radians per second. So this is the answer for this question. Next, you have to find the relative amplitudes at the rotors. So for that, we are finding the relative amplitude, means I can assume this amplitude at rotor A as 1. That means we are measuring the theta, so it can be assumed as 1 radian. Next, you have to find the amplitude, relative amplitudes of AC and AB if AA is equal to 1 radian. For that, you can use the similar triangle properties. So you can consider a triangle like this, and which can be considered similar to this one, and this can be considered similar to this triangle, and these triangles can be considered similar triangles. So based on this, you can use the equations like the amplitude AA divided by LA will be equal to amplitude AC divided by LC1. So here the AA we have taken it as 1 radian, and LA value is actually 0.913 meter. So AC you are evaluating, and LC1 value you have obtained, which is 0.334 meter. So if you are solving, you will be getting the value of the amplitude AC, and this will be getting around 0.336 radians. So this is the answer. Sorry, it is 0.366 radians. So it is the answer that you are getting. And in similar way, you can evaluate the amplitude of the at the rotor B also. So that can be evaluated using AC divided by LC2, which is equal to AB divided by LB. So now we are having the value of AC, which is 0.366 radian, and LC2 value you are having, which is 3.452, and this AB you are evaluating, and this LB value is 0.548. So you can solve for this value of AB, then you will be getting this as 0.058 radian. So this is 0.058 radian. So this is the answer for this case where two node is happening. The frequency is 27.71 radians per second, and we evaluate also the relative amplitudes. Next, we will be taking the case when there is a single node, that is actually based on the values of the other combination of LA and LB that you are getting after solving the quadratic equation. So there was another pair where LA you are getting, which is as 4.821 meter, and the LB corresponding LB value was 2.893 meter. So here LB is coming within the range of L2. So this is actually L2, which is 4 meters. So this LB is lesser than L2 4 meter. But here L1 was around 1.247 meter only, but here LA is coming greater than that. So this will be giving you the case of a single node where only one actual node will be within the section. So this happens when this rotor A and rotor C are rotating in the same direction and the rotor B is rotating in the opposite direction. Then you can draw the variation of this amplitude of this theta variable across the rotor and the shaft as shown in this figure. So the actual node will be obtained at this point. So this is the point and that will be given by the value of LB from this rotor B. And this is an imaginary one which is actually based on this projected one, and that value we will be getting from this LA, which is 4.821 meter. So here also you have to find the natural frequency of this kind of torsional vibration. For that also you can use any of the equation as I mentioned. So here I will be using omega NB, which is equal to QB divided by IB. So this QB you can evaluate similarly, which is GJ divided by LB. So here G value is 84 into 10 raised to 9, J is pi by 13 into 0.04 raised to 4, and LB is 2.893, and IB value was given, I think, which is 50 kilogram meter square. Then you will be getting the value of omega NB as 12.06 radians per second. Here the frequency will be getting like this. And in a similar way, you have to evaluate the amplitude of this theta at the rotor locations also, that is AA, AB and AC. So here also you will be considering the similar triangle. So here AA amplitude divided by this length, that is the LA. And similarly AC amplitude divided by this distance. So this is LC1. So in previous case LC1 was actually L1 minus LA, but here LC1 is actually LA minus L1. So you can evaluate that LC1. And similarly you can relate to the other one, that is AC divided by LC2. So this distance is actually LC2 and that equal to AB divided by LB. So I can write those equations, which is AA divided by LA equal to AC divided by LC1, where this LC1 is equal to LA minus L1. And similarly AC divided by LC2 is equal to AB divided by LB, where this LC2 is equal to L2 minus LB. So you can use this equation and you can find the relative amplitude. Here also I am assuming this AA value as 1 radian. Then you will be getting the value of AC. Here AC will be getting as 0.741 radian, and the value of AB at the other rotor end you will be getting as 1.937 radian. So based on this values, actually we are getting this kind of plot. Then only this will be coming like this. So in this kind of torsional vibration of this given system also, we have evaluated the natural frequency, and also we have located the nodes and also the relative amplitudes of this torsional vibration at this rotor locations. So this is the way how you can solve a simple problem from this torsional vibrations of 3 rotor system. So you can take some time for revising all these things to learn and understand properly. So hope you understood this problem, and thanks for watching.